Good afternoon, ladies and gentlemen. In this short video, I'm going to do the preparation problems for both practice C and practice D of chapter 17. The ones for practice C is on page 627. All right, so let's start with the first one. It's number 32. How long does it take a total charge of 10 coulombs to pass through a cross-sectional area of copper wire that carries a current of 5 amps? So let's talk about that. First of all, what do we mean by cross-sectional area? Hopefully you're watching the videos that I'm recommending, and you'll notice that an electrical current can go through something that can carry current. So it has to be a conductor that conducts electricity. So copper happens to be a great conductor. And in your textbook on page 613, there's a good table that says factors that affect resistance. So what is it that's going to resist the current from going through? Okay, so there's length, cross-sectional area, what kind of material, copper or iron, and the temperature. So here's the one cross-sectional area. So we're talking about how thick is your conductor, okay? The bigger the conductor, what's the difference going to be? Well, let's look at the equation of what current exactly is. So I draw your attention to this handout that I made for you on the back side. On the back side, what exactly is electrical current? Well, electrical current is the passing, the movement of charges, of electrical charges. Okay, so current is charge over time. So at what rate do those charges move? Okay, so at what rate do those charges move? And we have that it's the charge divided by time. There we go. That's our first part. All right, so in our problem, in our first problem, they give us the capacitance and the charge, which is the units is coulombs, and they give us that the area carries 5 amps. So how long does it take to get through that particular copper wire? Here's what I wrote down for that problem. They're asking us how long does it take? They give us the charge, Q, and the units of Q is coulombs and the current. Now current, we always say current is I. I should look up why that is and let you know why that is. Let's see, why I. I'm going to look that up, why I. I've never wondered before, it just is. All right, so I'm going to write that down. So current is the Q, the charge, over how much time. Okay, that's all it is. So we have the current and we have the charge. So we want to know what the time is. So we can do a switcheroo. But if you don't know what I mean by switcheroo, we can multiply both sides by delta T, cancel out, and then I divide both sides by I, and I end up with delta T is equal to the charge over the current. Okay, so let me start that. We started with the current is the charge over the time. And so that's what I meant by switcheroo. If you have just one variable and then a fraction, you can just switch these, because that's the same, it's true. All right, so here we go. We have here 10 is the charge, 10 coulombs divided by amps. So we have 5 amps. 5 amps, and I don't need a calculator for that. 10 divided by 5 is 2, and that'll be 2 seconds. So I want you to look up what the units of amps are, and you'll notice that it's going to be current per second. Okay. All right, so that's the first one. So that's just 2 seconds. Let's go to the second question. A hair dryer, like a blow dryer, draws a current of 9.1 amps. I'm going to go ahead and write that down here. Here we go, number 33. Start translating the problem as we go along. All right, so it says that the current is 9.1 amps. Okay. The question is, how long does it take for 1.9 times 10 to the 3 coulombs of charge to pass through the hair dryer? It's kind of similar to the previous one. So we know the charge is 1.9 times 10 to the 3, 1.9 times 10 to the 3 coulombs. I'm just going to move that over with 2 more. So I have 1900 coulombs. So how much time? That's the first part. How long does it take? Same thing. All right, so same thing. I start with my first equation. The current is, by definition, how much charge over time. So therefore, the time is the charge over the current, just like it is above. So I've got 1900 coulombs and I have 9.1 amps. See what that is? 1900, just faster than they doing the scientific expression. Okay, I got 208.791, and that would be seconds. So maybe you want to convert that to minutes because I don't know how many that is. Let's see. I'm going to divide that by 60 because there's 60 seconds in a minute. There we go. That might be a little more reasonable. 34.798798 minutes. So it's about 34, say 30. Oh, did I move it over to a right? Did I do that right? 34. If I got that right. Did I divide that by 60? Oh, look at that. I divided it by 6, not 60. That's why I got that wrong. So this needs to be divided by 10. Here, let's go back to 208. Do this right. Enter. Okay. Divide that by 6D, 60 seconds per minute. Now I got 3.478. So it's about 3.5 minutes. All right. So it takes about 3.5 minutes to get 9 amps or that much charge to get to 9.1 amps. Now the next question though says, how many electrons does this amount to of charge represent? How many electrons? So part A is the time and part B is the number of electrons. So how many electrons does that represent? So I draw your attention to back to your textbook, and we looked at this chart in the last chapter on the bottom of page 560, page 560. Okay, here we go. We know exactly how much charge is in one electron. Is negative 1.6 times 10 to the 19 coulombs. I'm going to write that down. I do not have that memorized. So one electron is 1.60 times 10 to the negative 19 coulombs. So if that's what it is for one electron, and we know how much we're talking about here, I'm looking for my highlighter. This is how much charge we have. The question is, how many electrons is that? Well, if this is the total amount of charge, and this is the charge right here, charge per one electron, then all we have to do is take those two numbers. How would I take those two numbers? The secret is always to make the units turn out. So if I take this number of coulombs and I divide it by the coulombs per electrons, the downstairs comes up. What does that mean? Well, let's say this is C over 1. C over 1 divided by C and then the number number of electrons. Then that's the same thing as C over 1 times the electrons over C, and my C's cancel out. Now, think about that. So I'm going to take the 1.9. So the number of electrons is going to be 1.9 times 10 to the 3, or I should have put 1900. Well, coulombs over 1.6 times 10 to the negative 19 coulombs per electrons. Okay, so I'm going to write that. 1900 coulombs, 1.6 times 10 to the negative 19 coulombs per electrons. That's going to tell me how many electrons. Because my coulombs cancel out and I end up with how many electrons. All right, so let's see what that is. I got 1900 divided by 1. Now let me use a parentheses to make sure. I got parentheses. 1.6 times 10 to the negative 19. Bring that down. And I get a really big number because it should be a lot of electrons. So now we know exactly how many electrons. 1.1875 times 10 to the big 22. 22 electrons. That's how many. So you can, with our significant figures, it's about 1.2 times 10 to the 22 electrons. All right. So this is before we get to electricity. We're thinking about exactly how many little electrons are going through. Okay, so that's the end of the problems for practice C. Let's move on to practice D, which is on page 628. I'll turn the page here. Okay, turn the page here. All right, so now we're actually starting to work with current, voltage, and resistance. All right, so I'm going to draw your attention to, again, this page right here. So the big thing, did I write it down? Well, I guess it's just in this table right here. All right, well, I'll go through this with you. All right, so current is represented by capital I. The units are amperes. Now here's what I was telling you to go look up. Ampere, and ampere, we say amps for short, amperes, is actually a coulomb per second. Okay, that makes sense? Coulomb per second. That's what an amp is. Okay, resistance, the units of resistance is in ohms. Ohms. So maybe that should look like an omega to you, because it is. It's an omega in the Greek alphabet. So we say ohms. And resistance is volts per amp. So how much volts and how much amperage, you divide those two and that gives you resistance, how much resistance you have. Okay, and you've already seen potential difference. Voltage is in volts, which is, is joules per coulomb. So joules of energy per coulomb of charge. All right, and then here's a summary of the other one. So here's potential energies in joules. What's a joule? It's a Newton meter. What's a Newton? Kilogram meters per second squared times meter would be kilogram meter squared per second squared. Okay, and volts, joules per coulomb, we just said that. Farads, that's your unit for capacitance. Farads is a coulomb per volt. Current, I just said above, is amps, which is coulombs per second. Resistance, volts per amps. And then power, we're gonna get to power in the next section. Okay, here's what I was looking for. What is a voltage? What is the voltage? The voltage is the product of the current times the resistance. Current times the resistance. Okay, and then the next chapter we'll do power is just current times voltage, or voltage squared divided by R. So this is another way that it's represented that may or may not help you. I didn't see this until I started here at the high school. I just had these memorized, that V equals IR. That's all I need to know, right? V equals IR. If I divide R to both sides, and I know that the current is V divided by I, which here we have here. Okay, so R is V divided by I. So V is equal to IR, and R is equal to V over I. And what's the next one left? I. I is over here, and so that would be V over R. So this may or may not help you. I just stick with this two, V equals IR and P equals IV. All right, so we're going to go with V equals IR. So those are the basics here. We'll start with number 40. Number 40. Okay, this one I didn't pre-write here. Okay, nichrome wire. So that's a type of metal that's a conductor with the resistance of, let's see, this is number 40. This is for prep for practice D. Okay, on page 628. All right, so the nichrome wire with the resistance of 15 ohms. So R is equal to 15 ohms. Here we go for omega. And what do they tell you? Connected across the terminals of a 3-volt flashlight battery. Okay, so they're telling us that the voltage is 3 volts. 3 volts, but yes, I noticed it's two significant figures. Okay, so what does that look like? I'm going to go ahead and tell you guys that the symbol for a resistor is like so. Well, let's see, like this. Okay, that's a resistor. Shows a resistor. Okay, that's a resistor. And it says here that it's connected across the terminals of a battery. So I already showed you earlier that here's a symbol for a battery or power supply. So this is how I'm going to show them connected. Okay, so I got 3 volts here, and it's connected to a resistor of 15 ohms. 15 ohms. So there's going to be a current. There's going to be a current that's going to go around and round and round and round. All right, maybe this resistor could be a little LED light, little LED bulb. If so, because LED bulb has resistance, if so, then it'll light up. Okay, Now, something that's interesting is if we say the current goes like so, that means the electrons are going in the other direction. Why do I say that? Well, electrons are negatively charged, right? So this is the difference between physicists and electrical engineers, the positive one. So if the negative isn't going to one direction, then they're like positive are going in the other direction. There's nothing positive that's moving the other direction. This is the confusion where we're like, wait a minute, what direction is the electron flow versus the current? Okay. All right, so I have a flow of electrons coming out. Now the question is, how much current? Oh, I'm sorry, here you go. How much current is in the wire? How much current? So I want to know what the current is. All right, I happen to have memorized V is equal to IR. That's all you need to know. Voltage. This is the voltage. This is current, which is in amps. And this is resistance. Resistance. All right, so this, by the way, is in volts. This is in amps. And this is in ohms. Okay, so V equal IR. That's all you need to know. All right, so they want to know what I is. So if I divide R to both sides, then I get I is equal to V over R, correct? Dividing R to both sides, I get V over R is I, and that is in here on that table. Okay, so let's see, I'm going to take volts, which is 3 volts, divided by 15 ohms. 15 ohms, and volts divided by ohms is amps. So 3/15. 3/15, what is that? 1/5, right? 5 times 3, that's 1/5. 1/5, which is 0.2. 0.2 amps. I like when I don't need my calculator. So I have 0.2 amps. So that's how much current is going to go through. All right, pretty straightforward. Let's do the next one. How much current in 41? Number 41. How much current is drawn? Here, I'm going to fold the page so we can have it right on top. Here we go. Here we go. How much current is drawn by a television with the resistance of 35 ohms? Oh, I stopped right away. Resistance is 35 ohms. That is connected across a potential difference of 120 volts. Okay, V is 120 volts. All right, and they want to know what the current is. What's the current? Okay, start with V is equal to IR. I divide R to both sides. R to both sides, and I get the current is V over R. Okay, so I'm just going to put the voltage, which is 120 volts, and my resistance is 35 ohms. I don't have that memorized. 70, let's see, 120, clear. 120 divided by 35. There we go, 3.42857 amps. I'm going to say how many significant figures I have here, 2. I'm going to say 3.4 amps. There we go, 3.4 amps. Again, this is just another application like the previous one of V equals IR. All right, the last one I like because this is actually what you will see in little resistors, and there's an actual color code. I didn't bring it ready for me in the book. It'll tell you, and I don't have that memorized, each of those colors means something. So for a 1, a 2, a 3, a 20, a 30, a 40. So this is, looks like black, green, black. And then the very last one is the tolerance level, which means it's plus or minus 10% or plus or minus 5%. The more expensive ones would be plus or minus a smaller percentage, how close the resistance really is. Okay, so I'll look for that chart and point that out to you, but you can see that in your textbook what the color markings are so that when people can look at it and they can figure out, oh, this one's a 20 ohm resistor, this is a 2 ohm resistor, it's a 5 ohm resistor, and then the tolerance one is the last color band. All right, it says calculate the current that each resistor shown below would draw when connected to a 9-volt battery. Okay, so looks like just like this again. Here's my battery and here's my resistor. That's all that is. So let's do number 42. Number 42. All right, so the first one, let's see, it tells me it's a 9-volt battery. So V is 9 volts. And A, put here AR, the resistance is 5 ohms. Is 5 ohms. I'll go ahead and write down the other ones. B is R is 2 ohms. And the last one, R is 20 ohms. Oops, R is 20 ohms. Okay, we want to know how much current. Again, how much current? So what is the current equal to? And just like before, current is equal to V over R. Okay, now normally I always want you to show me the first equation. So you better have at least somewhere there, on the page. Then you can go to this. All right, so V over R is 9 volts. 9 volts over 5 ohms. 9/5. What's 9/5? 9 divided by 5. Exactly 1.8. 1.8 amps. That's how much current. Now let's see what happens in the 2 ohms. I is equal to V over R. I have 9 volts over 2 ohms. I don't need my calculator for that. 9/2 is 4.5. 4.5 amps. Okay, 4.5 amps. And now we're going to go bigger this time. So notice, as you go to a smaller resistance, you're going to have a larger current. Okay, larger current. All right. And then the last one, let's see, we got V over R, got 9 volts over 20 amps. Oh, I can just move that over, right? That would just be 10 times less. Be 0.45. I think when I don't need my calculator. 0.45 amps. And that's it. So notice, the bigger the resistance, the same battery, the smaller the current. This is going to become important to you as we start moving into resistors in series and resistors in parallel, and what happens and when it can be dangerous, when you can get shocked because there's too much current going through you. I'm going to be giving you a handout to show you that current is actually what can kill you, not voltage. All right, so there you have it. Be sure you review just that voltage is equal to current times resistance. Voltage is equal to current times resistance. All right, see you guys later. Let me know if you want to meet with help, if you need any help. All right, see you later.